Hello, Painguri.
Sure.
We can start.
Okay, sir. Okay. Good morning to everyone. I'm happy to welcome all the participants on CERT 2-week FTP on in deep learning approaches. So our resource person session is going to be Dr. R. Thangarajan, Professor and Head, Department of Information Technology, KEC. He is having more than teaching and 15 years of research, and his research interests includes critical computer science and natural language processing. More than 50 research national and international, currently guiding scholars in Anna University, Chennai, and 6 scholars completed PhD under her guidance. Organized various seminars, conference, symposium, STTP, SDP, workshops sponsored by BRNS, CTE, DB, Infosys, PC, in different topics including national workshop in AI and deep learnings in association with Leading India. He delivers games and laws of artificial intelligence, machine learning for healthcare equipment design, learning models, machine learning frame techniques in healthcare applications, social IoT, recurrent neural networks, speech recognition, Monto, algorithms, social IoT, etc. He has completed 3 research projects, namely speech recognition for Tamil language by Tamil Virtual. Second project, high performance computing and private, sponsored by AEC. And third one, Python and problem sponsored by UG and one funded by in Science DST New Delhi. I'm happy to welcome Dr. R. Tangarajan, Professor and Head Department of Information, to us to share his expertise in linear intelligence. Sir. Thank you, sir.
Good morning, participants. It is my pleasure to meet all of you on this FTP program. Is my voice clear? Okay, okay. Say, for example, if something you find it difficult, means say for example, this breaking, please inform me on. Okay, right. So now I continue with my session. So this session is about some basic essential mathematics for machine learning. Okay. To course on so for on machine learning, actually there are some mathematical background that are needed, like for example the linear vector spaces. Okay, there is a linear algebra, matrix theory. Okay, optimization techniques. Okay, some bit of calculus is required, and also probability is also required. So the things that are required, them in short. Okay. So this will be a brief because today's session morning and also the afternoon session I'm going to take. Okay. So I may not be able to get into the complete details of it because this is a very vast subject. Okay, and lot of courses are available elsewhere also, like for example on NPTEL and on Coursera also you will find lot of courses that are available. Essential mathematics. Now let me think that our session.
Voice is breaking, sir.
Breaking.
Yes, sir.
Is it okay now?
Now it is okay, sir, but it is too low, sir.
Too low. I don't know why. Wait, just a minute. Yeah, can you see my screen now? Is my screen visible?
Yes, sir, it is visible.
Okay, okay. Okay, so I'll start. Since actually, I think I have any. So as I said before, so I'll be dealing with this topic. Okay, in the forenoon I'll be talking about the basic linear algebra, matrix theory, and matrix decomposition algorithm, and dimensionality reduction. Okay, so this will be the topics that will be covered in the morning. In the afternoon, we'll have a basics. We'll see optimization and we'll see support vector machines. So basic calculus is actually, I think, needed because this have some so which you can, I think you can easily follow. Okay. Next comes the topic. So what is machine learning? Okay. So it is an application of AI. Okay. So mostly we say that nowadays we hear the term artificial intelligence. So it's a broad term. Okay. A very broad term used. Wherein machine learning is actually a part of AI wherein we learn from data, that's all. So in machine learning what we do is we use data, okay. So we use data or I will say learning from data. Okay. So like your traditional computer, if you look at your traditional computer, so what you do is this is explicit programming. You do explicit programming. So where what you do, you give instructions by program, input data and program together are given to the computer. The computer executes the program step by step, and what it does, it produces an output. Okay, so it does some processing. Okay, the processing is totally governed. The processing is controlled by the program. Okay, what to do, how to do. So that is explicitly told by the program, and the input data is read from the input device, and you get the output. Okay. So this is traditional explicit programming. But when it comes to machine learning, what we do is there are certain tasks. Okay, there are certain tasks which computers cannot. For example, okay, any recognition, for example, voice recognition, face recognition, speech recognition, language recognition, whatever it is. So these topics are mostly, these tasks are mostly done very well, very easily by a human being. A human being can very easily recognize the voice of his a colleague or friend or parent. Okay. Similarly, a human being can recognize a photograph, even if the photograph is, say, for example, it is not in a good quality, or we can recognize face in, say, dark environment. Okay, when there is poor light. Okay, but when it comes to computer things, okay, we do learning from data. So what we do is we give both input data and the output data, output label. We know what is the output we want. We know what the output we want. So we give input data along with the output label. So we train. So here the computer is trained, and the computer is left to guess what it is. So computer will now guess what the function is, what the program or function. So the function is actually what is that program. Okay. So the computer will the program. Okay. In programming, you have what the computer you have to do on the data. Here you give the data and the output label. So you give these two together. The computer will looking at this data and label, output label, will guess the program. What is that program? Okay, or guess the function. Okay. So that is machine learning. So short, I will. So in a nutshell, we can say that this is what is machine learning. So in machine learning, we have this two. One is important. That's all. So when it comes, so there are a couple of things that you have to know, that there is something like supervised machine learning algorithm, supervised. Then you have unsupervised, semi-supervised, okay, reinforcement learning, okay, and then finally we come to deep learning. So what is supervised machine learning? Okay, so this is the previous slide is a case of supervised machine learning, because here you see we give the input data along with the label. So what you give as input is the input data x of I, and you also give the output. X of I is the input, the corresponding desired output is y of I. So where I will be from 1 to up to n. You can give up to n labels, n number of inputs. Okay, and n can be as large as, say, for example, 1 million or say 10,000 or whatever it is. Okay, so you give a pair of data. There is the input along with the output. Okay, desired output. The computer is left to guess what the function is. Okay, this kind of learning is called supervised learning. Okay, so this is supervised. Okay, unsupervised is when you are given only a training data. You are not given a label. Say here you are given training data and label, but here you are given only training data. But it is guess what the data. So when this is the case, so generally what happens is you need a lot of training data. Okay, but whereas here in supervised learning, machine learning, because we are giving labels also, so the amount of training data is not so much, required so much. Okay, but here the training data has to be enormous. Okay, then only the computer can do some clustering. Okay, it starts similar items. So starts identifying similar items. Okay, so this is basically what happens in actually whenever a child is actually learns. Okay, child means when a child is say a child is less than 1 year old. Okay, when a child is less than 1 year old, say we don't teach the child with labels. Okay, so the child is born, and the moment he is opens the eyes, actually he can see. Okay, he can hear, he can see, he can hear. So now what happens is he does not know anything about the world. Okay, so what he starts doing is he starts identifying structures, similar structures. That's all. He will identify what a round thing means. Okay, the square environment is string. Okay, and as a result of it, that their learning occurs. Okay, so he can now say when he looks at a world, he can know that this is what. Say that's how actually children they learn to to see the face. Okay, learn the face. They can identify the face of the mother. They can identify the face of another person. Okay, so only by looking at it and knowing, because repeatedly they are doing. Okay, that's what I told you. You need a lot of training data. You need a lot of training data. So you have to repeatedly they are immersed in that environment. They are again, and as a result, they do a very wonderful job of learning by themselves. That is unsupervised learning. That is, they do a lot of clustering, and they can group things. They can say this is similar, this is not that. Okay, they can identify what is what and what is not. Okay. Then semi-supervised is actually you may be given a training partial label, some labels which are not given. Okay, so it is something which is between this supervised and unsupervised machine learning. Then learning. This is a different kind of, nowadays we use it. So here what we do is say what is the difference between this and this, first one and this one. Okay, the first one you have to give a pair of data. So you have to give input x of I, and you have to get the output also. You have to give the output also. You have to give both input and output. The machine will generate an output y cap of I. For the input x cap, for the input x of I, it will generate an output y of I, y cap of I. But the actual desired output is y of I. So it is also given. Now what the learning algorithm does is, the learning algorithm simply tries to find the difference between these two. And y of, and this is error. And using this error, there are so many other say metrics, like you can have a you can take a mean squared error value, okay, or logistic error value, whatever it is. So based on that, you try to minimize the error. When I try to minimize So you try to see that the y cap, the guess what the computer guesses is almost similar to y of I. In that case, this error will be minimum. Okay. So what we do in supervised learning is we give training data and labels, and the computer generated output is compared with the output label, and the error is calculated, and the error is tried to minimize, making the guess of the computer y cap of I almost equal to y of I. So this for every set of reinforcement, some playing chess. So when you are playing chess, so when is that you are going to win? You know only at the end. Okay, so at the end when you checkmate, when you checkmate your opponent's king. Okay, when the opponent's king is checkmated, you are winning. Or if your opponent checkmates your king, then you are lost. Okay. Or if, for example, some due to some reasons, say for example, if it is not possible to checkmate both of them, then it becomes a draw. Okay. So whether it becomes draw or a loss, losing the game or winning the game, at the end, you know that when you play chess, you make a lot of moves. You make a lot of moves. You start here. Then, as time goes by, you make a lot of moves. Generally, you also have a clock in a chess game. You have to make the moves fast. Then, finally, at the end, you know that whether you have lost or won. Okay, and whether you lose or win depends upon your intermediate. Okay, your intermediate. Example, the intermediate make x of I, x of 1, x of 2, x of 3, x of 4, and maybe here it is x of n. I make n moves. So the first move, second, I don't have right or wrong. I don't know, because I know that only at the end that I have won. Okay, if I won, then it means that whatever moves I have made are right moves, are the right moves. Whatever moves I have made are right. So that is when you have won. Okay. Some moves, but there are no labels for each and every move. For each and every move, there are no outputs. Whether this move is right or wrong, it is not known. You don't know. Okay. Well, you know only at the end that if you have won, that means that you have made the right number of moves. Okay. So for such applications, okay, so we do a reinforcement learning wherein what we do is the computer, so the system when it learns, it makes a set of moves such a way that finally you get two things. You win, that means you get a reward, or you get a penalty when you lose. So whether you get a penalty or you get correct. In jargon, they call it action. So the actions are reinforced when you get a reward, and when you get a penalty, the actions are actually they are not reinforced. Okay. So so based on the ultimate final reward and penalty, you will be your machine learning algorithm will work. Okay. So as a result, when you play chess, so you have to play chess for a long time. Okay, then ultimately you come to know that what are the right moves and what are the wrong moves. Okay, you get an idea. Okay, now so these are the moves that will enhance. These are the moves that will not. This is one application that you can take here. Another application that I can take in reinforcement learning is, say, for example, a cab driver. Okay, so you have a taxi or a cab driver. So the cab driver is actually new. For example, nowadays, why I'm taking example of cab driver is because nowadays you have autonomous car. Okay, so so we don't have a driver. We have a computer that actually drives the car. So in that case, a passenger is getting into the car. Now that passenger, you have to drop the passenger, say for example, at the airport. Okay. Now for that you have to drive through the city traffic. Okay, finally reach the airport. So there are so many things that you have to consider. Okay, say the amount of time that is left with. Okay, so because say flight is at 11 a.m. Okay, flight is at 11 a.m. The person gets into the car at say 9 a.m. Now you know that you have to be at least 1 hour before the flight, so you have to go at least drop him. 1 hour to reach the airport. Say for example, the airport is say 6 kilometers away. Okay. In that case, you know, you have to take a lot of things into consideration. Say for example, the traffic. Okay. Even though nowadays you have a lot of Google Maps and aids available, so you have to make decisions. You have to take decisions regarding which route to take, how to go about, so that you reach the airport at 10 a.m. Okay. And when you are driving, also you have to take be careful that you are not doing a rash driving. Rash driving means not driving very fast, so that the police is stopping you and you are getting fined, or you are getting into some accident or something like that. Or sometimes the customer may not feel convenient. Okay. So all these things count. Okay. So when you drop the customer at the airport at say 10 a.m., then the customer will give you. Okay. So that tip will tell you whether you have done a good job or not. Okay. Because you have reached the airport, but whether you have done a good job or not depends upon the tip of the customer. Or nowadays, when you know that the Uber, the star rate, the customer give you a rating, star rating. So now if the customer gives you a 5-star or a 4-star, then you know that you have done a good job. Good job means in terms of driving safely, arriving at the right time. Okay. So like that. So in that case, these sequence of actions, these are the sequence of actions that have given you a reward. So now you know that is, now you learn. Okay. So these are the right actions. Okay. For my job. So like that, you can go on taking examples. Okay. You can take the example of a bearer at a hotel. Okay. So again, the bearer will do a lot of service to you, and finally you give him a tip. Okay. So the tip tells him whether he has done a good job or not. Okay. So what is that I'm telling you is ultimately based on the final reward or penalty. Okay, you are able to work. Okay. So so that is called reinforcement learning. Okay. Now comes to deep learning. Okay, deep learning is actually a neural network, artificial neural network. Okay, but the difference is that the artificial neural network in the olden days, actually they were not very deep. The number of hidden layers were limited. They are called shallow networks. Okay, the number of layers are limited, but they had certain problems at those times. The algorithms were not developed. The people had a problem of say in the propagation, that is you know that there's a back propagation algorithm. Okay, so it's all gradient based methods. Okay, so that's what we will see. That's why the topic is important to you. Now because of the gradient, that is the derivatives you find, they become saturated. So in that case, what happens? Neural network, nodes of the neural network, they either shut down because of vanishing gradient, because the gradient has become 0, and sometimes exploding gradient, the gradient has become very large, and therefore the output becomes 1. In either case, what happens is no learning takes place. Okay, because in neural network learning, so the weights of the learning are Wi is actually updated based on delta value. Okay, so Wi plus 1 is equal to Wi, so plus or minus some delta W. The gradient, if this gradient becomes 0, then Wi plus 1 is equal to W of I. Okay. Similarly, if this becomes 1, then W of I will become saturated. When it becomes saturated, the neuron always becomes 1. It never, when it is 1, again you see that there is no learning. Okay. So the learning stops. Okay. And that was the reason why people had this problem of introducing more and more number of hidden layers, because they could not introduce that. Okay. Because the more number of hidden layers, the more was the problem with the vanishing gradient. Okay. So, but now that's the reason that actually where was not continuous. You see, a lot of time the neural networks, people lost interest in neural networks. Okay. But in 2006 onwards, actually some beautiful algorithms have come place. So that can address the problem of this vanishing gradient. Okay. And as a result of that, now again there is a renewed interest in neural networks, and that's the reason why we have now we have deep learning, meaning more number of hidden layers in a neural network architecture. Okay. So, and because they have overcome the problem of vanishing gradient, vanishing or exploding gradient, and as a result, now you have algorithms that you can train deep layers as so layers that have say 100 hidden layers. Okay. So as a result, now you see that's the success of this deep learning algorithm. Okay. So this is was just a gist of learning algorithms that you have today. Okay. So this is, I already told you that the history. So you can see that 1960 that those came about. In 1990s, this data mining, reinforcement learning, base learning, actually it's base learning. It's not base learning. Okay, BaseNet learning. Then these are machine learning algorithms. So next comes in 2000 the SVM or the kernel-based methods. So this we'll see in the afternoon. Okay, and statistical learning, and now you see 2010 onwards people started using deep learning and CNN along with generative adversarial networks. Okay, so these are our deep learning algorithms. Okay, coming to the topic, the role of mathematics. So why you need mathematics? Okay, so for example, as I already told you that because of this matrix theory, linear algebra, single variable and multivariable calculus, okay, gradient based optimization methods, basic probability, and these are very much required. These are very much required. So a strong input is required on this topic, and that's why actually say before learning machine theory, machine learning, before learning machine learning, if this student has say enough knowledge in this topics, then it will be easy for him to understand. Okay. So that's why this particular topic has been taken. Okay. And so this when you have this knowledge of this basic essential mathematics, then you will know that what can be done and what cannot be done. Okay. So that's both are, it helps you in both the cases. What you can do, what machine learning can do, and what you cannot do with machine learning, both you can take. Okay. So that I will, as we go by, you will understand. Okay. Okay. So these topics are understand the behavior of machine learning tools theoretically. Okay. So what we try to do is we try to put them together and see. Say I think say you might have learned them in a piecemeal approach. Actually, you might have already learned about them. Okay. But or as part of learning machine learning, you might have learned those mathematics. But when you learn them in a sequence, then you will know that you can see how these different concepts put together, how they work. Okay. Okay. Now with this we'll start with vectors. Okay. So now that's the introduction part of it. Now we enter into the topic. So what is vector? So vector is something that is very much essential in our machine learning. So there are domains. So this is maths domain. Okay. And this is machine learning. So our machine ML. Now you see that in ML we use a lot of objects, is it not? Entities. For example, we talk about in a natural language processing, we talk about words. Okay. And you talk about features. in machine learning. Okay. So what you learn a lot of topics you learn like this. So what is that they are actually when you want to manipulate them mathematically in the math world? So what are they are? They are represented as vectors. Okay, so vectors are they are actually mathematical objects. Okay, so which are used in which are used in machine learning for certain manipulation. Okay. So what is a vector? Okay, so vector is actually, you might have seen because in school days we learn what is a vector. A vector is, you might have seen that is an arrow like this. Because we know in school we have been talked about what is vector and scalar. Okay. So you know that vector has magnitude. Say for example, this name of the vector is v. The vector v has a magnitude. It has a magnitude and also has a direction. It also has a direction. We represent it as like this. So this is what this is how you have been known to use a vector. Okay, and scalar just has a magnitude. It doesn't have direction. So scalar is just a number, pure number. Okay, okay. I'll not call it v. I'll call it by some other name. I'll call it say a. So just a value a. Okay. So, like for example, if you can take the temperature at a particular point in a place, that is a scalar value because the temperature doesn't have direction. Okay, so it is a value. Say for example, the temperature at this location is, say for example, today it is 95 degree Fahrenheit. So when I say that, then it is a value. It is only a value. It is not a doesn't have direction. When it comes to a vector, say we talk about velocity. So velocity has two things. It has a direction in which direction you are going, and also it has a component called speed. Speed is the magnitude of the velocity. Say I am traveling at 100 km north. So then I will say that this is velocity because 100 kilometers per hour towards the north. Okay, then when you talk about velocity, the velocity also tells you the direction. Okay, not only the magnitude, the direction. So this is how physically you understand a vector. Okay, and a vector, say for example, you have two vectors. Say another vector is, say this is w. Okay. Now say now you see these vectors are objects. Now how to do operations on this vector? So how do you add two vectors? So say how do you add two vectors? What you do is you take how to add vectors. You just take the vectors, put them together. For example, they take this vector v, and you take this vector tail of that vector w and put it here. Then what you do? You join this tail with this head, and this is v plus w. Okay, so this is how you do vector addition. Okay, this is how you do a vector. So like that, and what you do? What about vector subtraction? You reverse the direction of w. Okay, you make w as minus w. When you w is this direction, when you reverse the direction, it becomes minus w. Okay, then you can now put the tail together, and now you can put the tail. Now you say this is v, and this is minus w. Now this is my v. Actually, it is v plus of minus w. That is v minus w. Okay. So you can do a vector addition or a vector subtraction like this, or you can just scale a vector. For example, this is vector v, and to this vector I can multiply a scalar. I can multiply a scalar. Say I want to make it 2 times bigger. So this is a vector which is multiplied by a scalar a. The vector is same, the direction is same, but I multiplied by a scalar a so that it becomes bigger. Okay, it scales up. Okay, depending upon the value of a. Okay, so like that I can multiply a vector by a scalar. I can add vectors. I can subtract vectors. So vectors are some objects. Vectors are objects on which I can do set of operations. I can do some set of operations. Okay. So this together is actually it is a vector algebra. That's all. We call it vector algebra. That is, you are doing some operations on vector. Okay. Now I told you that the machine learning features like words or features or say for example any objects in machine learning, you can represent it conveniently you can represent it as vector. Okay. But the vector, we are not going to talk in terms of arrows like this. Okay. But we are going to see the vectors in an abstract manner. So abstract manner, what is a vector? Okay. So vector is actually it is a for positive number n, that is n is a real number. Okay. Positive real number n integer. So we say r of n. R, you know what is r? R is real number. Okay, real number, domain of real number. Okay. So which is we suppose we are talking about a complex number, then we use c. But in our discussion, we are not going to talk about complex number. We are going to talk about only real numbers. So real numbers, you know, the numbers on a real number line. Okay. So 0, okay, and plus infinity. So you have numbers. Any number on this line is called a real number. Okay. And n is the number of such numbers. Okay. So n dimension. So n dimension. So if this is one dimension where n equal to 1, suppose I can have one more axis like this, then it's n equal to 2. And if I have one more axis like this, then n equal to 3. Okay. So so we can pictorially represent n equal to 1, 2, 3. But when n becomes 4, 5 and all, we cannot represent it pictorially because number of dimensions of 4 you cannot visualize. Okay. But theory, you can say n can this vector can have n dimension. There can be n dimension for that vector. Okay. So and it is represented as a tuple. As a tuple, it is represented like this. So where x1, x2, x3, so these are components of the vector. Okay. So x1, x2, x3, they are components of the vector. Say for example, if I call this vector as x, okay, then x1, x2, x3, they are the components of the vector x. Okay. And r power n, so this is, I told you, the real number, domain of real number, r power n is called the n dimensional real coordinate vector. Okay, or simply we can call them vector. Okay. And these are the components as I told you. Okay. And the elements, these individual elements, actually they are scalar. These individual elements are scalar. Okay. So to understand them, you have to have an idea like this. So for example, if you take a 2-dimension, so I take a vector, say V. Now, how this V is represented as, so you have to just take this value. This is say x component, or I will say x1 component, and this is x2 component. So these are two components. So it's a 2-dimensional vector V is equal to x1 comma x2, x1 comma x2. Now each this x1, x2, they are components. So how they are components? So this is the value. So this vector is represented by this value. And this I will put it as capital X, sorry, capital X1, capital X2. That is the axis, and this value is small x1, component of the V in the capital X1 axis, and component of V on the capital X2 axis is small x2. Okay. Now I can represent this vector V as a tuple x1, x2, where x1 and x2, they are components of V on the respective axis. Okay. And these are actually numbers, because you know that these two arrows, they are number lines. So these are two real numbers. This is real. This belongs to so this belongs to a real number, one of one dimension, and this again another real number of one dimension. Okay. So where each component of the vector, they are real. Okay, they are real numbers. Okay. Now this is a vector in 2 dimensions. Similarly, this is a vector in 3 dimensions. Okay, so 3 dimension is a vector. And similarly, you can have n dimension vector in r power n. Okay. So up to 3 we can visualize. After r power 4 and r power n, you cannot visualize, but actually they are vectors. Okay. So any vector whose magnitude is 0 is called a 0 or null vector. For example, you see that this point is actually a null vector. Okay, this is because here both the magnitudes are 0, so therefore this is a null vector. So null vector is represented as 0, 0. Okay, right. So this is a null vector. So so it's an identity. Okay. So for example, so when we talk about mathematics, we talk about mathematical space where you have elements. What are the operations you can do on those elements? Okay. Then you have the identity operators. Say identity means 0 is an identity. That means you can add that null vector to anything and it doesn't change. Like in our number theory, you see 0 is there. So 0 is it's an important part of it. Okay. And similarly 1. Okay. For example, if you take a number a, then 1 by a is the inverse, and when you multiply a into 1 by a, then you get 1. That's the identity. Okay. Likewise, here also we have this is a null vector, and similarly you have identity vector, that is who's actually you can say that this is say when I come to matrix, I'll explain that. Okay. So right. So here you will talk about basis. For example, basis is this is one basis. The basis is the two bases are 0, 1, 0 and 0, 1. So this is the basis. Okay. So I'll come to that later. Okay. Okay. This is okay. So yeah, here you can see. Okay. So here this is a standard basis. Okay. So 1, 0, 0, 1 for a 2 dimension. So this is the standard basis for 3 dimension, 3 axis. Okay. And this is the standard dimension ratio. Basis, standard basis for n dimension. Okay. When I say basis, I will come to that later. You take a pair of them, they will be orthogonal. Orthogonal means they will not be they will be perpendicular. Okay. This is one thing basis. This is another basis. When you take them together, you see they are perpendicular. Why they are? How do you say they are perpendicular? When you do that, I'll come later. When you do a dot product, with two vectors, if they are perpendicular, then the dot product is 0. When you take a dot product of these two things, it will be 0. Okay. So that I'll come later. Okay. So for the time being, you just understand that these are the base. Another name is basis for axis. Okay, I told you you know that this is x-axis and this is y-axis, something like that. We imagine like that, but this axis is called 1, 0, and this axis is called 0, 1. Okay, in 3 dimension, you will have one more axis in this direction, and that will have a different value. Okay. Now these are the operations you can do on 2 vectors. So you need to know the algebra. So for example, this is one vector, this is another vector. So what are the operations you can do? You can add and subtract vectors. Okay. So when you add and subtract vectors, what you do? You do a item wise, component wise addition. You do a component wise addition. The first components of both the vectors are added or subtracted. Second components are pairwise added or subtracted, and the nth components are added and subtracted. So this is component wise addition. When you do a multiplication, yeah, this is what is called a dot product. So when you do a multiplication, you see that we take this, is it not? Say we take a sum of x1 y1 plus x2 y2. We take a product of component wise product, and then we add them up. So you get xy, and this xy is not multiplication of 2 vectors. It is called the dot product of 2 vectors. Okay. This is the dot product. Okay. Next is finding the length of the vector. So I told you that this is a vector. So there should be some mechanism to find what is the magnitude of the vector. What is the magnitude of the vector? The length of the vector, or norm of the vector. The other name is norm. To find the norm of the vector, you take this. That's all. You take the elements pairwise, square them up, and add them up. That gives you the length or the norm of the vector. Okay. You say two vectors are equal if their components are equal. If the components are equal, then I say that two vectors are equal. Okay. Now I come to the graphically. You can see how this dot product, that's multiplication of vectors, that is a dot product, and the cross product, they work. Say when it comes to say dot product, say you have two vectors. Say for example, I'll take this vector, my axis. This is one vector. This is another vector. I'll call this V. I'll call this W. Now I take a dot product. So I'll say V dot W equal to. So what is the V dot W? V dot W is nothing but the projection of V onto W, or the projection of W onto V. The projection of V onto W, okay, that is this part, or the projection of W onto V, they are what is called the dot product. Okay, right. Okay. So if this is V and this is W, then this V dot W is this one. So the dot product is always a scalar. The output of a dot product is a scalar. Okay. So what you do is, if this is V, say for example, V is represented by two axes, say V1, V2. If W is represented by two components, W1, W2, then V dot W is equal to, if you write it in vector, so this is what I told you in a graphical mode, but in a vector notation, they are represented as V transpose W, V transpose W, and always remember that, sorry, here actually it's V transpose. Generally vectors should be written in a column way. If I say a vector V is a vector V, then this is the right representation of a vector V1, V2, where V1, V2 are components. Okay, and this is W, then W1, W2, they are components. Okay. Now when I say V transpose W, then what you have to do is, you have to take the transpose of V, means convert the V into rho. When you convert the V into rho, it becomes V transpose looks like V1, V2. So, and W is taken as it is, W1, W2, okay, which is equal to. So now you do multiplication, isn't it? So this is a matrix multiplication. So this is 1 cross 2 dimension. This is 2 cross 1 dimension. So the result will be, the 2 will go away. So the result will be 1 cross 1, a scalar. So what do you do? V1 W1 plus V2 W2. So that is a number. That's a pure scalar value. Okay. So therefore the dot product of two vectors has to be represented like this. So when you represent a vector in row, you have to put a transpose sign on it. If you represent it in a column, then it's a vector. Okay. So this is the dot product of two vectors V and W. Okay. Graphically, you can also say that this is the angle between the two vectors, theta. Then I said this is a projection. This dot product is the projection of V onto W. In that case, what is this projection of? Okay. So you see that the projection is, what is this value? This value will be, this is a right angle triangle. So V times, so this is cos adjacent side. So V dot cos theta, that's all, V cos theta, or I'll say V into W cos theta. Sorry. So you have to multiply V and W, and you have to multiply by cos theta. If cos theta is 0, if theta is 0, then cos theta is 1. In that case, the two vectors are parallel. We say that if the two vectors are parallel, then the total projection of V is on W. The total projection of V is on W. In that case, the cos theta will become 1 because theta is 0. Okay. When V and W, they are perpendicular, we say they are orthogonal. Because here now you see that this right angle. So here when you take the projection is here. It doesn't fall. Okay. Therefore, the dot product of V and W will be 0. V dot W equal to 0 since theta equal to 90. When theta equal to 90, cos 90 will become 0. When cos 90 is 0, automatically V W cos 90 becomes 0. So then we say that the two vectors are perpendicular to each other. So this is how you say a graphical representation of this. Okay. Right. Now I'll come back to the example what I was dealing. I told you in 2 dimensions. This is axis 1, 0. This is axis 0, 1. I told you that these two are perpendicular. How they are perpendicular? Now just you take the dot product. Okay, 0, 1 into, take the dot product. So what is that? 0 into 1, 0. 0 into 1 plus 1 into 0. So you see that the dot product between these two axes 0. Then you say that this angle is 90. So these two are perpendicular to each other, or they are orthogonal. Okay. Right. So this is how you have to understand the graphical implementation with the okay. So this is what the dot product is. So the dot product of two vectors is the magnitude of x into magnitude of y, again multiply with the angle between x and y. Okay. Cross product. Say cross product generally you will come across in physics, but not here. Generally, I think maybe here we do not use cross product. So cross product is, say for example, if this is one vector, say for example E, and this is other vector, let's say M, then what is cross product? The cross product is generally perpendicular. So cross product is something which is perpendicular to both the plane of E and M. E and M, if they are two vectors in a plane, then the cross product will be something which is perpendicular to them. Okay, and cross product is a matrix. Okay, I told you dot product is a scalar value, but cross product is a matrix. For example, here you take, and how do you put them in a mathematical form is, so I will take the same example like before. If say E is E1, E2, and M is M1, M2, then what is E cross M? E cross M is, you have to put it like E M transpose. The transpose will not come here, the transpose goes here. So it is, what is it? Now what is E? E is E1, sorry, when I say E, it has to be a column. Okay, what is M transpose? M1, M2. Now you take a product. This is 2 cross 1. This is 1 cross 2. So 1 and 1 go away. So finally, what you get? 2 cross 2. You will get a 2 cross 2 matrix. So what is that? E1, M1, then E1, M2, E2, M1, E2, M2. So you get a 2 cross 2 matrix. So and this is and this is what this is. So it is perpendicular. It is perpendicular to both E and M, right? So this is cross product, and this cross product is represented as sine. Magnitude of x into magnitude of y into sine of theta. Sine of theta means sine of this angle. This angle is theta. If you flip a vector, for example, if E we make minus E, then this sign of this will become down. Then this will become minus E cross M. Okay, if you flip it. So these are the operations that you can do on vectors. Okay. Right. So generally, now you see these are the operations. What operations you can do? You can do addition, subtraction. Only addition. Subtraction is a special case of addition. That's all. You can do addition. You can take dot product. You can find the length of the vector. You can find whether two vectors are equal. You can also find the dot product of the vector. You can also find the cross product of the vector. That's all. These are the operations that you can do on vector. You know what is a vector. So what is a vector? This is a vector. So this is the norm of a vector. Okay. So like that, you have vectors and the operations. You also have a null vector. Null vector is 0, 0. Or if it is 2 dimension, I am talking about 0, 0, 2 dimension. If it is n dimensions, then you will have n number of zeros. Okay, this is for Rn, whereas this is for R2. Okay, so this is a null vector in R2, this is a null vector in Rn, and along with all other vectors and these operations, so totally it forms a vector space. Now, what is this? We call it a vector space. Okay, and vector space on a real field where the numbers, individual components are real numbers. Okay, so it's a vector space on real field. You can also have a vector space on complex space. Okay, so that depends upon, but for our applications of machine learning, vector space on real fields is sufficient. Okay. Now this is another important concept that you have to know. Okay, and that is linear combination of vectors. Okay. So what do you mean by linear combination of vectors? Right. So this I will demonstrate with a graph. Sorry, with a demonstration. Say, for example, you take vectors like assume that they are perpendicular. Now, can you represent this vector in terms of this vector, or can you represent this vector in terms of this vector? This is what you mean by a linear combination. So I'll call this vector V1. I'll call this vector V2. Can you represent V1 in terms of V2 or V2 in terms of V1? If you are able to do that, for example, if I am able to say that V2 is equal to some constant times V1. V2 is some constant times V1. Okay. Now what is from this equation you can say that I can represent V2 in terms of V1 by multiplying V2 by V1 by a constant. Now with this equation what you can do, you can say V2 minus A times V1 equal to 0 from this equation. If you bring this side, it becomes 0. Now what is the meaning? So here there is here you have 1. Okay, actually it's 1 times V2. So here you have some constant C1, coefficient C1 into V2 minus some another coefficient which is where C1 is equal to 1 and C2 is equal to minus A plus C2 times V1 equal to 0. Okay. If this condition is true, okay, for any set of vectors, okay, like for example here in this case there are two vectors, and the condition is true where C1 and C2 they should not be 0. Should not be 0. Okay, see C1 and C2 if they are 0 it's trivial. Okay, it's trivial. If C1 and C2 is 0, trivial, so it will be 0. But actually C1 and C2 not equal to 0, and if you have this condition, then I can say that vector V2 and vector V1, they are, this implies V1 and V2 are mutually, they are dependent, they are linearly dependent. They are linearly dependent. Okay, so this is what actually it means, right? So when vectors are linearly dependent, so this I can generalize for any, say I can say for example n vectors C1 V1 plus C2 V2 plus Cn Vn. If it is equal to 0, then I can say that these vectors V1 V2 up to Cn, they are linearly dependent. Okay, they are linearly dependent. Why? Because I can just take any one of them to the right hand side. Okay, so for example, I take this to the right hand side, then what happens? It becomes C1 V1 plus C2 V2 plus Cn minus 1 Vn minus 1 equal to, when this goes this side, it becomes minus Cn Vn. So now you see that I can represent Vn in terms of linear combination of V1 to Vn minus 1. Linear combination of V1 to Vn minus 1, I can represent Vn. Then I can say Vn can be represented as a linear combination of all these vectors. Okay. Therefore, they are linearly dependent. Therefore, they are linear. This is the meaning of linear dependence. This is the this is what you mean by linear dependence. Okay, so that's what I have given here. Okay, say you have a vector like. Okay. Now, for example, like what I told you, before. So, say for example, this is some axis V, and I have another vector, say W, or say V3. I have another vector V3. Okay. Now you see that V3, can I represent V3 in terms of V1, V2? Yeah, you can represent them. Just to draw something here. This is the component of this. This is another component. Okay. So some component C1 times V1 plus some component C2 times V2 equal to V3. Okay. So that means this set of vectors V1, V2, V3, they are linearly dependent. They are linearly dependent. That's the meaning. Okay. Right. Now you know that, or this is in terms of figures I told you. Suppose if you take this as 0, 1, and 0, 1, and this as vector, this vector as 1, 0. Then what I can, this is this value is C2, this value is C1. Then I can say that C1 into, what is this, 1, 0 plus C2 times 0, 1 equal to C3. Now just multiply, what happens? C1 comma 0 0 comma C2. When you add, you get C1 comma C2.
Hello.
So this is your vector. Okay. Yes.
Good morning, students.
Hello.
Kekudha? Answer me.
Madam, is it audible?
Kekudama?
Yes, ma'am.
Hello.
Yes, sir.
Is it audible, madam? Any
Yeah,
problem?
Yes, sir.
Hello.
Wait, we will remove that.
Anyone answer me?
Sir, interpreter disturb
It is
ஆகுது
audible?
sir.
புரியலைங்க மேடம், என்னங்க?
Students?
Sir, voice இன்னொரு வாய்ஸ் வருதுங்க சார்.
It is
டிஸ்டர்ப்
audible.
ஆகுது.
There is
இல்ல,
a
இப்ப யாரும்
cross
mic on
step.
பண்ணிருக்காங்க, அதனால தான். If all of you can mute the mic, I think the problem will be solved.
சில்வியா இங்க வாங்க. ம்.
Someone has unmuted their
சில்வியா
mic.
கேக்குது சில்வியா, நேத்து கேட்டுச்சு பாரு, செக் பண்ணு.
Sir? Sir,
Hello.
we continue, sir. I removed that person, sir.
Somebody actually unmute the mic, so that was a problem. Okay.
Okay, sir.
Otherwise, so far, any disturbance? You had any problem?
No,
No
sir.
problem, sir. No problem.
No. Okay. Okay. So I think so what you understand, no? So I was just demonstrating this. So what do you mean by linear combination? So this is one vector. This is another vector. And linear combination of these two is vector V. So that's what I am trying to say, that suppose V is equal to C1, C2 is a vector, then V can be written as C1 into 1, 0 plus C2 into 0, 1. So that will be equal to C2, 0 plus 0, C2. So this is two matrices, that's all. You add the two matrices, what you get? C1, C2. So that's what I was telling you, that this is what the vector V is. Okay, so this is linear combination. So what you need to understand in linear combination is the scalars, they should not be equal to 0, but their linear combination with the components of the vector, if they add up and if you get another vector, then you say that this set is a linear combination of the set. Okay, and similarly here I can say that this is again another linear combination in 3 dimensions. In 3 dimensions, this is another linear combination, and this is a linear combination in n dimension. This one in n dimension. This is in 3 dimensions. This is in 2 dimensions. Okay, so I think now you understand. Okay, now I think you will be able to understand what is this. Okay, what is this? So these are, with our previous discussion about a dot product, I told you that these are axes or bases. Okay, these are bases. Okay, these are bases, and this vector V is a vector with in a basis of 3 dimension, where these 3 are basis vectors. So naturally they have to be perpendicular. Okay, they have to be perpendicular. This is 1, 0, 0. This is 0, 1, 0, and this axis is or I will say this axis is 0, 0, 1. Now in this 3 dimension, if you put another vector, say a vector, this is vector, and this vector can be represented as a linear combination of all the other 3 vectors. Okay, so the 4th vector is a linear combination of the bases. Okay, now you know what is the basis and what is not a basis. Okay, right. So with this we go to the term linear independence. Linear independence. Okay, as I told you the definition, if this is true, when C1, C2 up to Cn are not 0, if this is true, then we say that they are dependent. They are dependent. If this is not equal to 0, then I will say that it is linearly independent. The vectors are linearly independent. Okay, like for example, here this is a linear dependence. Can you say how? These two are linearly dependent. LD, linearly dependent. Why? Because one vector is 1, 1. Another vector is 2, 2. These are two vectors which are linearly dependent. Why? Because I can put this in a 2, 1, 1. So same vector 1, 1 multiplied by a scalar 2 gives you this. So these two vectors, these two vectors, they are linearly dependent. But whereas this vector, if you take 1, 0 and 0, 1, they are not linearly dependent. They are not linearly dependent, or they are linearly independent. They are Li. Li means linearly independent. You cannot represent this as this, or you cannot represent this as this, vice versa. Okay, so that I say that they are linearly independent. Now what about this? Can this 3 be linearly dependent? Linear independent? Yeah, you have to just see whether you can represent any one of them, or just you take a pairwise dot product. If the pairwise dot product is 0, then you say that sorry, not pairwise, that I have to come later. The only thing is that whether you will be able to represent the other vector as a combination of, can you represent this vector as a combination of these two? Just to try. You have to just multiply by a scalar. You have to multiply this by a scalar, and you have to add these two vectors, so you get this vector. Okay. Or is this vector a combination of these two? If you are able to do that, then we say it is linearly dependent. Otherwise, linear independent. Okay. Right. Now, when I talk about the basis, when I talk about the basis are linearly independent. At the same time, they are orthogonal. So this is the basis. This is the basis. Then the property of this basis is they are linearly independent. These three should be linearly independent. At the same time, they should be orthogonal. They should be orthogonal. That means the angle between them should be 90 degrees. The angle between any two bases, if you take, should be 90 degrees. So when you have vectors of this, then we say that they are linearly independent and orthogonal. The orthogonality comes when the angle between them is 90. Okay, then they are orthogonal. They are linearly independent when you cannot represent one as the other. Okay. So when vectors are orthogonal, automatically they become linearly independent, because when they are orthogonal, you cannot represent this as a vector of this. Okay. So that is orthogonal vectors, when you take, they automatically become linearly independent. Right. Okay. But if you take linearly independent vectors, they are not orthogonal. They may not be orthogonal, but they will be linearly independent. But they may not be orthogonal. Okay. Right. So this you have to take. Okay. So this is what I was mentioning about orthogonal vectors. So we need to represent feature vectors as a linear combination of a set of linearly independent vectors or orthogonal vectors. In machine learning, you take a vector which is represented as a combination of a set of orthogonal vectors. Okay, and we need to represent all the vectors in the feature space as our data set as a linear combination of those vectors. So if you take all the vectors in a data set, so you will have a data set. For example, say we take a 3-dimension. So in a 3-dimension, you may have a data set like this, a 3-dimension, in which you may have a data set where you may have lots of vectors. So, use different colors. You may have lot of vectors, different. So in that case, each one is a vector. Each one is a vector which can be linearly expressed in terms of this three green axes. I'll call them V1, V2, and V3. So all the colored arrows, what I put here, they can be represented in a linear combination of V1, V2, V3, where V3, V1, V2, V3, they are the basis of the data set. Okay. This you need to understand. So this we will be talking about when we come to dimensionality reduction. So why we are doing this? Because we always want to reduce the dimension. Okay, we want to reduce the dimension. Say, for example, if we from a 3-dimension you may want to go to a 2-dimension, or from say n dimension we may want to go for a say some dimension less than n. So that I will come later. Okay. Now comes the basis. So I already talked about basis. So I think it will be clear. What is basis? So here you see this is the basis in R2, this is the basis in R3, This is a basis in R power n. Okay. Not only this, see, you can take a matrix also as a field. Okay. So these are in a field of this is in a field of real number, but whereas if you take a matrix, okay, a m cross n matrix, that itself can be represented as an element. For example, this is one basis. Okay, so you have one here, all of elements are 0. This is one here, all of it. So there's no way you can take this matrix and take this matrix and represent this matrix in terms of this. So you can always say that this matrix and this matrix, they are linearly independent. They are alike. They are linearly independent. And when you take a product of them, they will be 0. Automatically they will be 0. So they are orthogonal. So you see that we are extending the idea of orthogonality from vectors onto matrices. Okay. So matrices are they are is another object in our linear algebra. Okay. So again you see that this set S, it forms the standard basis for a matrix of m cross n order, and where every element of this matrix belongs to a certain field. In our case, we take the field as real number. Okay. So this field could be a complex number also. Okay, that's also possible. Okay, and now this is what is called the basis. Now the number of bases you have is what is called the dimension of that particular vector space. The number of bases is the dimension. Okay, so in this case the dimension is 2. In this case the dimension is 3. In this case the dimension is n. Okay. So like that you can have the dimension of the matrix. So this is 2 n, okay, and the dimension of this when you talk about matrix is m cross n. The dimension is m cross n. Yeah. Say you need not have just the vector space need not be just your vectors. It could be matrix. It could be a polynomial also, an nth order polynomial. For example, if I say if I take an nth order polynomial, for example, a power xn plus b power xn minus 1 plus some no, I will not use ab, I will use some other number. I will say a1 x power n plus a2 x power n minus 2 plus a3 x power n minus 3, like that, plus a1 x plus a0. This is a matrix, sorry, this is a polynomial, polynomial of order n, the highest degree is n, a polynomial of order n. Okay, where this coefficients a1, a2, a3, they are coefficients which are real. So now what is the dimension of this nth order polynomial? How many elements are there? What is the dimension? The dimension is n plus 1. Why n plus 1? This is n, and of course you have a constant here. Okay, a1 x1, then this is a0 into x0, x power 0, actually x power 0. So from x power 0 to this x power n, how many there? They are n plus 1. So for an nth order polynomial, the vector space of nth order polynomial will contain n plus 1 dimension. Okay. And similarly, a vector space of a polynomial which has infinite order, a polynomial of infinite order will have infinite. Generally, when you talk about all polynomials, you say take all polynomials. Okay, that is a polynomial of order 0, polynomial of order 1, a polynomial of order 2, up to polynomial of order n, where n can vary anywhere. In that case, you see that this vector space has infinite dimension. Okay, when you don't say, because n can go to any value, is it not? So from 0 order polynomial, 1 order polynomial, 2nd order polynomial, 3rd order polynomial, I can go up to nth order polynomial where n can go to infinity. In that case, the number of dimensions for this all polynomial will be infinite. Okay, right. Okay. Now just for example, so these are simple trivial bases. These are trivial bases which by looking at that you can say they are natural. Okay, but there can be other bases also which may not look natural. Okay, for example, here you take this example, In this example, you see that it's a vector in R3. It's a vector in R3 because there are 3 components, but the relation between this components is such that x1 plus x2 equal to minus x3 equal to 0. That is x1 plus x2 minus x3 equal to 0, or I can say x1 plus x2 equal to x3. I can say like this. In that case, what happens? So what is my, how can I represent any point? Any point can be represented as x1, x2, and what is x3? x3 is x1 plus x2. Okay, if you take x as 1, then this has to be 0. It cannot be 1. So this is 0. Then in that case, x3 will be 1. So this is one axis. Okay, this is one axis. What is the other axis? If I take x1 as 0, then x2 should be 0. Sorry, 1. In that case, this is 1. So this is another axis. Here is first axis, second axis. Okay. So you see that. So what is even though it is described in a 3-dimension space, but you see that the third dimension is dependent upon the first 2 dimensions. Therefore, effectively the number of bases required is only 2. So it's only 2 dimensions. Okay, it becomes a 2 dimension. That's what I told you. The dependence between the components. Okay. So here you see that the third component depends upon the first 2 components. Then in that case, it is merely a 2 dimension. Hence, the basis of S is, these are the 2 bases, and the dimension of the this vector space S is 2, even though it is described in a space with R3. Okay, now I think you should be able to know. That means that you are describing the vector in a 3 dimension, but actually this vector space S is falling in a 2-dimensional space. In a 3-dimensional space, it is actually falling in a plane. Okay, that's the meaning. Okay, right. And this is another vector W1, x1, x2, x3, where x1 should be equal to x2 equal to 3. This is the condition we put, where x1 should be equal to x2 equal to 3. So what is that basis? You can have only basis you can have 0, 0, 0. So as you know, 0, 0, 0 is the null vector. So leave it. The another value is 1. If you put 1, then it becomes 1, 1, 1, because x1 should be equal to x2 should be equal to 3. That's the condition you impose. In that case, even though you express this this space in 3 dimensions, but actually it is a 1 dimension. It is falling on a line. Okay, so the dimension of W is a 1. It is falling on a line. So this is this is the dimension of what is this S, and if you take it W, all should be 1. Then it is actually a dimension which is falling on a line which is diagonal to this, and this is that which is diagonal. X1 should be equal to x2 should be x3. In that case, this is the line which is at 45 degree. Okay, in the 3-dimensional space, and all our points are lying in this particular space. Geometrically, if you want to look at it, you have to look at it in that way. Right? Okay, so I think I will not get into this. Yeah, next I will get into an important topic, that is eigenpair. Okay, so what is the eigenpair? Okay, so this is again another important topic that you have to remember, that we do this often in our machine learning. Okay, so what is this eigenpair? So just I will explain first, then I will get into the topic. Say you have a vector space like this, say for example 2 dimension, you take 2 dimension. So you have a vector, this vector, sorry, I will use a different color. Okay, you have a vector, assume it is B. Okay. Now what I do, I operate on this vector. I operate on this vector. So what are the operations that I can do on the vector is, one, I can do scaling. I can do a scaling, or I can do a rotation. I can always do a rotation. Okay, so you know how to do a rotation. So if I do a rotation, then what should I do? So scaling means just you have to multiply a with the v with some value a. Okay, that's simple. That's scaling. What is rotation? Rotation is that you have to multiply this vector v with a matrix. And what is that matrix? And that matrix is a rotation matrix, and that you know what's the rotation matrix. It says cos theta. If you want to rotate it by angle theta in 2 dimensions, cos theta minus sin theta, cos theta. So this is the matrix, and if this matrix, if I multiply v, okay, with this matrix, then what I get? You know, v is a v1, v2. Okay, so v actually consists of v1, v2 components. If you multiply, then you get v1 dash, v2 dash, and if you see that v1 dash, v2 dash, it will be rotated. It will be rotated by an angle theta. If I do this, this is a matrix M. When I multiply with this vector v, I get this vector v dash, and this v dash is rotated, but it is not scaled. It is rotated. Whereas if I just want to scale, I can multiply the v with just a scalar value. It will just do that. Now, what is that important thing is about this matrix? What is the relation between this matrix and this particular vector v? Okay, if this matrix happens to, what is the relation between M and V? If you apply on V, and V happens to be, that is, on applying M to V, and that results in V being scaled by a value lambda, not rotated. So here you see, here in this case, the V has been rotated. Okay, so this is V which has become V dash, which has been rotated. But here, what actually we do is, there's a vector for every matrix. That's a vector. For that, if you apply that matrix on that particular vector, okay, and in that case, what happens when you look at the result will be the vector is not rotated, but only the vector is scaled by a value lambda. The vector is simply scaled by a value lambda, not rotated. Okay, then it is called an eigenvalue pair. Okay, so this, in that case, we say that V is a eigenvector of M, and lambda is the corresponding eigenvalue of V. Lambda is the corresponding eigenvalue. Okay, so this concept is actually, this is what is called the eigenpair. Okay, so for example, this is a 2-dimensional matrix, so there will be two eigenvalues. Okay, because that is a two-dimensional, so there will be two eigenvalues, lambda 1 on this direction, and another direction lambda 2. Okay, so there will be two directions. There will be two values. Okay. Right. So this is what I told you. So this is what is called the above relation tells us when the matrix A applied on V, it then scales V by an amount lambda without rotating the V. Without rotating the V, it just scales the V by a lambda value. Okay. So, and these are set of properties about the eigenvector and eigenvalue. So in that case, I told you V is an eigenvector. V is an eigenvector of A, and lambda, in this case, lambda is the corresponding eigenvalue of V. Okay, so you may have more than one eigenvector for which you have lambda. So this I would like to demonstrate in a different setting. For example, why we do this? Why we do this? Okay, so you should know why we do this, because that will be clear when you come to principal component analysis. So why we do this is because, if, for example, you have an you have an axis like this. We call it x1, x2, and I have some data. Now you see the variation of the data in x1 and x2. This is the variation in x1. I'll call this variation as sigma x1, and there's a variation in x2 also. See, it varies from here. In x2 it varies sigma x2. So you find that the data is spread across x1 and x2. Now you may think that these two components are really essential. Okay. Now what you do is, now you have to find this eigenvalue problem. Now what you do is, you apply this data set to you find the eigenvalue in such that what happens is, now you get two different bases. There is two different eigenvector, two different eigenvector, say V1 and V2. These are two different eigenvectors. So that V1 will be like this, and V2 will be like this. And you see the eigenvectors, they are always orthogonal. They are always orthogonal. And this eigenvectors, they are two corresponding eigenvectors. And what is the implication of that lambda value, that eigenvalue? It says the norm of V1 is, say, lambda 1, that is the length, and the norm of V2 is lambda 2. That means there is a scaling that you are doing in the direction of V1 and the direction of V2. Okay. Now you find that here, actually I have not drawn the figure correctly. So you find that the variation along this direction is very small. You find the variation along this direction is very small, but when you find the variation along this V1, it's large. That means what? That means V1 is the principal component of this particular matrix. Okay. Whereas V2 is just an outlier. Maybe it is a noise. Okay. So like this, we are able to get the values. Okay. So that's why this actually is a very, very important problem. This is why you find always finding this thing. Okay. So only thing is that say, for example, some properties which you can just read it, no problem. Say, for example, if A is a matrix, and if you invert A, if you have a inverse, for A inverse exists, then the corresponding eigenvalue will be 1 by lambda. If lambda is the eigenvalue of A, and if it is if lambda is the eigenvalue of eigenvector in A, then if V is the eigenvector of A inverse, then the corresponding eigenvalue will be 1 by lambda. Okay. And this can be raised to any power. Okay, say matrix power 1 into V equal to, so if I take a square of the matrix A and multiply by V, then I will get lambda square into V. So just square the matrix and the corresponding what you call lambda value gets squared for any value K. That is for a set of integers. K should not be, say, you cannot use a real number. I cannot use 2.3. Okay, 2.5. It should be Z. Z means real number. Integers. Okay. Then sum of eigenvalues of A. If you take the sum of, say, for example, A has 3 eigenvalues. A is a 3-dimensional matrix, 3 eigenvalues. Then what is the sum? Say this is A is a matrix, 3-dimensional matrix. Then what is the sum of A? Has 3 eigenvalues, lambda 1, lambda 2, lambda 3. What is the sum of them? Then the sum is just the trace. Just you take the diagonal elements and just add. You know what do you mean by trace? Trace is the sum of the diagonals. You take the sum of diagonal elements, you get the sum of the eigenvalues. Then what is lambda 1 into lambda 2 into lambda 3? Okay. So that is nothing but just take the determinant of A. Just take the determinant of A and you just you can find the product of the eigenvalue. Okay. If there are two eigenvalues of a matrix A, and if these two eigenvalues happen to be independent, not equal, lambda 1 is not equal to lambda 2, in that case the corresponding eigenvector, for this you have eigenvector V1, and for this you have eigenvector V2. If two eigenvalues are not equal, then the corresponding eigenvectors, they are orthogonal, or sorry, they are linearly independent. They are linearly independent. Okay, so these are some of the properties that you have to know as far as eigenpairs are concerned. Okay, and this is about another thing, that is eigenvalues of symmetric matrices are real. Okay, so when you take a symmetric matrix, you know symmetric matrix, a matrix whose this upper triangle is equal to this lower triangle. If these two are equal, then we call a symmetric matrix. And a symmetric matrix can be n cross n. You cannot have a symmetric matrix with m cross n. Okay, so the rows and columns will be same. Then the diagonal elements will be there. Then the opposite and the lower triangle should be equal. In that case, the eigenvalues are all real. The eigenvalues are real. Otherwise, the eigenvalues will be complex. Okay, so the eigenvalues are real in case of a symmetric matrix. Then for a symmetric matrix, there exists an orthonormal basis. There always exists an orthonormal basis, means the corresponding eigenvectors, they are orthogonal. The corresponding eigenvectors, they are orthogonal. Okay, and if A is symmetric, then we can decompose A into a diagonal matrix P D P transpose. Okay, so where D is a diagonal matrix with eigenvalues in diagonal, and P is the eigenvectors. P is the eigenvectors of A okay, the eigenvectors, corresponding eigenvectors of A. Okay, and this is the transpose of that. Okay, so this formula is a special case of a symmetric matrix. Okay. For a pseudo, for not symmetric matrix, we don't. If you take a non-symmetric matrix, in that case, what will happen is we have to go for another thing, SVD, singular value decomposition. So it's a more general case. Okay, so SVD is for any n cross m matrix, but whereas this should be only for a symmetric matrix n cross m. Okay, right. So that's you have to remember. Similarly, as I told you, like vectors, matrix can be orthogonal. Matrix can be orthogonal if their columns are pairwise orthonormal. Say, for example, if you take a matrix like this, and if you take this column and this column, this is one vector, this is another vector. Just take the dot product. If it is 0 for every pair, if it is 0, then we say that this entire matrix is orthogonal matrix. The entire matrix is a orthogonal matrix. So pairwise they are. Each column pairwise they are orthogonal. Okay, right. Okay, eigenvalues of orthogonal matrix have absolute value 1. You have to see that this is another property, that eigenvalues of orthogonal matrix will have an absolute value 1, and the determinant will be either +1 or -1. Okay. If Q is orthogonal matrix, and Q inverse will be just its transpose, that's all. If you have a matrix Q which is orthogonal, I want to find the inverse, you don't have to work, just take a transpose of that, it becomes the inverse. Okay, that means Q inverse into Q inverse will be 1. Q transpose will be I. I is the identity matrix. Okay. If Q is orthogonal matrix, then null of Q is the 0 vector. So I come to the singular value decomposition. So before I go to singular value decomposition, I just I want to take a small break for just 5 minutes, because I've been talking for a long time. So what I will do is I will just from this point I'll just take a break for 5 minutes. Okay, then we'll join after 5 minutes. Is it okay?
Okay, sir.
Okay, I think we can start again.
Okay, sir. We will start, sir.
Okay. So any problem so far up to?
No problem, sir.
No
So
problem.
voice is audible, sir. It's okay. Everything is okay.
Oh, everything's okay. Okay, right. Okay. So participants, if you have any queries, means you can also you can put it on the chat box, okay, or you can also unmute and you can also ask. So now I go on to the singular value decomposition problem. So as I already told you that so you have a matrix A which is symmetric. In that case, I told you that a symmetric matrix will be of n cross n, and the upper triangle and the lower triangle will be same. Okay. In that case, all the eigenvalues will be real. Okay, and they will have an real orthonormal r power n orthonormal basis. Okay, so where it is something like this, I can let you know how you can do it. Okay, so if I want to put it this way, so say for example you have a matrix A, okay, so which is a 3-dimensional matrix, so 3 cross 3. So it is symmetric, means that these values are same. Okay, that is, for example, I can just for your sake I can have, and this is A11, A12, A13, this is A22, A33, A21, A23, A31, A32. In that case, A12 will be equal to A21. Okay, so these two will be same. And similarly, A13, or in general, I can say Aij will be equal to Aji. So this is symmetric. And at the same time, the diagonal elements. Okay, so this is A11, these are diagonal elements. A22, A33. They are diagonal elements. Diagonal elements will be here, and whereas these opposite elements A1, A12, A21, they will be same, equal. A13 will be equal to A31, like that. So suppose A is a matrix like that, then what I can do is I can factorize. Okay, just like you can factorize ordinary number. For example, I give 15. You can always write it as 3 into 5. So how do you factorize a compound number? By primes. Okay, so it is factor of primes, 3 into 5. Similarly, a matrix can be factorized. Okay, this matrix can be factorized into P, Q, P transpose. Such a way that what is P, Q, and P? P. So P, this is P transpose. That's all. So where P is a matrix, okay, which is also n cross n, whose columns are eigenvectors. Whose columns are eigenvectors, means this is V1, V2, Vn. There are n eigenvectors of n components, and this Q is again a diagonal matrix whose diagonals are the eigenvalues. Whose diagonals are eigenvalues, and of course this is P transpose, whose this transpose of this, that's all. So whose rows are eigenvectors. So this is V1, V2, this is Vn. Okay, so this is the meaning. Okay, where lambda 1 is the eigenvector of V1, lambda 2 is the eigenvector of V2, lambda n is the eigenvector of Vn. So actually it is A into A times Vi equal to lambda I times Vn. Okay, this is the case when the matrix is symmetric and when the matrix is n cross n unsymmetric. So in this case 3 means it is 3, there will be 3. Okay. If it is n, then it will be n. Okay, so this is a special case. Okay, and when you look at these values, when you look at this diagonal value, you will find that the diagonal values are, other values are 0, the diagonal values are eigenvalues, and the eigenvalues will be in order. Say lambda 1 will be greater than equal to lambda 2, lambda 3. Okay, lambda. So in this case, it will be not equal to, it will be strictly greater than. Sorry, in this case, it will be strictly greater than. So lambda 1 will be greater than lambda 2 will be greater than lambda 3. So you will have n for a n dimensional n cross n matrix. You will have a n dimensional n cross n dimensional. What is that? Eigenvectors. These are, each eigenvector will be orthonormal. Each eigenvector will be orthogonal. And each each eigenvector will be scaled by this corresponding eigenvalue. Okay, so so from one basis you go on to create another basis. That's all. Okay, so from one basis we are transforming into another basis. So that's what we have done in this case. This is for the special case of symmetric matrix. Okay, now what to do in case of a real matrix? So sorry, any matrix R comma M. Okay, you take a matrix A which is not square, which is M cross N. So when it is M cross N, naturally it cannot be symmetric. Okay, and N cross N, because when M is greater than N or M is less than N, so this matrix cannot be symmetric. So if it is not symmetric, then how do you decompose? How do you diagonalize? Okay, how do you diagonalize? So that is the procedure, a common procedure called singular value decomposition. Okay, so what you have to do is, just if you are given A as M cross N, A is M cross N, you have to find A transpose A. Okay, what is A transpose A? A transpose, what is the dimension of A transpose? A is M cross N, A transpose will be N cross N. N. Okay, A is M cross N, A transpose will be N cross M. What is A? A is M cross N. So what is the resultant matrix? The resultant matrix, this M and M go away, then the remaining is N cross N. So A transpose A will have N cross, dimension N cross N, it becomes a square matrix. But it will not be, symmetric, but it will be a square matrix. And you also take A into A transpose. In that case, A is M cross N, and A transpose is N cross M. In that case, you will find this N will go away. So the resultant matrix will be M cross M. So now you see that you have beautifully N cross N matrix and a M cross M matrix. That is, A transpose A will be N cross M, N cross N. A transpose will be M cross M. Okay. Now on this, at this, you can perform the singular value decomposition. Okay. Now what is that actually we have to do is, say you can because it is now a square matrix. Now what we can do is, you can do a SVD, and of course when you do an SVD, what you will get is again this matrix A will be, when you do an SVD, you get 3 matrices where this is U, this is sigma, this is V transpose. Okay, where U is a matrix whose columns are eigenvectors of, I think, A transpose. Okay, the rows I will confirm that. The columns of U, they are the eigen vectors of A transpose, and V, whose columns are eigenvectors of A transpose A transpose A, and this is again our matrix which is contains diagonal matrix in 1, 2 up to what is this lambda n. So where this is these are the and when you just take the square root of this, we get sigma I. Okay, so which are the singular values? These values are called singular values, and you see that lambda, the sigma 1 will be greater than the sigma 2 will be greater than sigma n. Okay, and these square root of lambda 1, lambda 2, lambda n, they are called the singular values of A. The singular values of A. Okay, so this is a general case. Okay, yeah, so that's what I have told you. So when it comes to the dimension of the matrix, what is the dimension of U? Okay, the dimension of U, yeah, sorry, correct here. The dimension of U is M cross N. What is the dimension of A? M cross N. The dimension of U will be, because U consists of eigenvectors of what? Of A transpose, so this is M cross N. What is the dimension of V transpose? Dimension of V transpose is N cross N. What is the dimension of sigma? Because this is M, so naturally here you should have M into, and here it is N, so naturally here you should have N. So sigma, the singular, the diagonal matrix is not a diagonal matrix actually, because the dimension is M cross N. So it is M cross M into M cross N into N cross N. So naturally when you take the product, you will find that these two will result in N M cross N, and when you multiply with U, which is M cross M, these two will result in M cross N, sorry, N, M cross N. So naturally that is what E. Okay. Our only thing is that this sigma matrix is not a rectangular matrix, it is not a square matrix, but whereas U and V, they are square matrix. Now why do you find this? That is what actually our next thing we are going to discuss. We find that and here you see that, yeah, so V is the eigenvector of A transpose A. Okay, this sigma square is the eigenvalue of this Vi, and this matrix U, the columns of matrix U, they are the eigenvectors of A transpose. Okay, that's what I mentioned here also. Yeah, U is for A transpose, and V is for A transpose A. Okay, so like this. Okay, right. So why we have to do this actually? So if you want to have a geometric interpretation of this process, I told you that any matrix when you apply on a vector, any matrix if you apply on a vector, that creates two things. One, it actually scales. The two things it can do: scaling and rotation. Okay. Suppose if I take this basis, okay, which is perpendicular like this, and apply this matrix operator, then what I get is, see here both are same, the length of both the bases are same, the norm is same, but they are perpendicular, okay, in this angle. Now when I apply this matrix operation on this particular thing, then I will get something like this, wherein this is rotated. You see, this is rotated by a major axis. So now you see that scaling has been done. So now this, instead of being this, becomes sigma 1. Okay, so it has been scaled. Okay, and this is sigma 2 scaled by sigma 2. So therefore, what happens? This becomes longer. Which one? This becomes longer. Sigma 2 is greater than sigma 1, and this becomes shorter. And you instead of getting a circle, you get an ellipse. Okay. Now, not only that, this is scaling, effect of scaling. Now, what is the effect of those eigenvalues, that eigenvectors? Eigenvectors, they rotate. Okay. Now, instead of having in this direction, the ellipse goes in this direction. Okay. So this is the net effect of multiplying this operator A on this particular basis, what we have shown here. Now, this can be this is what happens when you directly multiply with A. But when you multiply with the, now what we have done, instead of A, we are using this. Instead of A, we have made a singular value decomposition, and we are going to multiply our basis. Okay. Now, for example, this is X is the basis we are trying to multiply. Okay. So this is transpose actually. This is transpose. So what we are trying to do is, first we are trying to apply V transpose. First we are trying to apply V transpose on X. So that's what we are applying here. On this we are applying V transpose. So that simply rotates. That simply rotates. So this does a rotation. Okay, rotation. And what does this do? This scales, because you know this consists of your sigma 1, sigma 2, sigma 3. So this will scale. So the sigma will scale this into this matter. So it is rotated and scaled. Okay. Then what happens? U rotates this in this direction. Now what you have to do? You have to rotate it back to the same direction. Okay. Okay. So that U does. So once the sigma scales, after that the U again rotates it back in this manner, so that it becomes like this. Okay. So this, when you do follow in a sequence, has the same effect of doing this. Okay. Now you will ask, so this is a geometrical interpretation of the SVD. Now you will ask why we are doing this. Okay. So why we are doing this is because we want to say one thing is finding an inverse of a matrix which is M cross N. A is M cross N. Now you cannot have an inverse of a M cross N matrix. Inverse exists only for square matrix. You cannot have a inverse for a rectangular matrix. Now, how to find the inverse of a rectangular matrix? So for that you have to do something called a pseudo inverse. We can always find a pseudo inverse. You can always find a pseudo inverse. So how do you find a pseudo inverse? So you just decompose it into SVD. Just invert. So we want inversion. Okay, you want to invert this. So you find A inverse. So you have to find A inverse is equal to, just invert this entire thing. When you invert this entire thing, what happens? These are orthogonal. U, V are orthogonal matrix. I already told you. So when you take orthogonal matrix, you know that to find the inverse, just you have to transpose. Just you have to transpose. So first you have to transpose this. So V. Then this is just a diagonal matrix, so nothing happens. So this remains sigma. And when you transpose this U, it becomes U transpose. So you have to apply from here. So transpose V, so that is V. So V transpose becomes V, and sigma unaffected. And U, when you take an inverse of U, just take a transpose of it. Because, why transpose? Because V and U are orthogonal matrix. When they are orthogonal, if you take an inverse, that is equivalent to inverse. Anyway, so when you transpose, it is equivalent to inverse. Okay. So now we got this. So this has to be A inverse. This has to be A inverse. That's all. So to find inverse of a rectangular matrix, we can use SVD. Okay. So this is the mathematical application of pseudo inverse. And another, say for example, here the same example they have shown that rectangular matrix. For this, you want to find a SVD, so you get a SVD like this. So this is a U matrix, a sigma matrix, and V matrix. Now, just take the transpose of this and put it here. This is V. This is V transpose. Take the transpose of this, put it here, V. This is not affected, remains as it is. Whereas what is this? This is U transpose. Take U and take a transpose and put it here. That's all. Now when you multiply again, you get A inverse. Okay. So, but this A inverse is not real, it is pseudo. It is pseudo A inverse. Okay. Another important application of this thing is low rank approximation. This is again a very, very important application of SVD that we always do. So what we do is, say for example, you may have a matrix which is very big. For example, I may have A, which is M cross N. There are M rows, N columns. Okay, and assume that these rows are your features. Okay, those are features, and N is your number of vectors in a data set. In a data set, these are the features, rows are the features, or I will take it like this. Rows are the number of vectors. Each row is a vector. Each row is a vector with n features. There are n features for each vector, so n features. So there are m rows with n features. So naturally m will be greater than n, and m is the number of vectors you have. And say for example, in a data set there are say 1000 vectors, 1000 records, and each record has say for example 20 features. So it is 1000 cross 20 matrix. So it's a 1000 cross 20 matrix. Now I don't want this. So what I want to do is I'll just take a SVD of this. Okay, so when I take a SVD of this, I get 3 matrices. This is U, sigma, V transpose. Okay, and the U has columns which are eigenvectors. Eigenvectors. There are m eigenvectors, m cross m eigenvectors of what? Of A transpose. And these here, this has whose columns are eigenvectors of A transpose A. So there are n eigenvectors. So it's a n cross m, and this you know it is a m cross m, and whose rectangle. So actually I should have drawn it a little thing. So like this. Okay. Rest of the items will be 0. So up to say for example we have some. This is m. So m is bigger. So m is bigger. Yeah. So it's natural, correct. So after that some. Okay. Now what you can do is, for example, I will have lambda m. Okay. Now what I have, say m is very big. Okay. M is say. Sorry, m is big, but actually the number of columns is 20. So actually there will be only 20. Okay, so other things will be ignored. So lambda 1, lambda 2, lambda 3, lambda 4, lambda up to 20 you will have. Lambda 20. Now what you do is, now this is not required. Actually we don't require. You know that this transformed feature will be having some space like this. So what we already seen. So it will have space like this, where sigma 1 will be negligible than sigma. Here you see that sigma 2 is greater than sigma 1. So that means this feature is more important than this sigma 1. Okay. Suppose there are 20 features. Okay. So I have sigma 1, sigma 2, sigma 3, like that up to sigma 20. Now in this case it will be like this. Some order. Now what I will do is I will say for example I may require, say I will take just first say 5. Okay, sigma 1 to sigma 5. Rest other I ignore. Okay. So in that case, what I do here, I just take up to sigma phi. Other things I ignore. So this is I take only phi. Okay. Now phi means what? This is phi cross phi. This becomes phi cross phi, and so this is already. So now what I have to do here, I have to ignore. There are m. There are totally m number of things, so which I have to ignore. So I have to ignore. I take only phi. Rest other I ignore. Okay, this I ignore. Okay. Similarly here, phi cross phi. So again, naturally this n has to be phi cross m. So again, I have to ignore. I will just take the phi rows. I'll take the phi rows. Rest other I ignore. So by doing this, what happens is I get a low rank approximation. I get a low rank approximation, and that low rank approximation is when you multiply them, you will get instead of you will get a m. So now what you will get is m cross 5 into phi cross 5 into phi cross n. So again this everything will go up, and the final matrix A will be again m cross n only. Sorry, this is n. Yeah, this is n. So therefore m cross n, but the values will not be same. The values are low rank approximated because I have ignored some of the eigenvalues. So the values will be changing. So I call this matrix A cap. Okay. So A m cross n will not be equal to A cap m cross n. Okay, where A cap m cross n is a low rank approximation of this. Now what is that I have to do is why I have done this is because this has lot of applications, especially you have ignored those some of the eigenvalues which are not significant, you have ignored them. That is one thing, and you have done a dimensionality reduction. This is what we say, dimensionality reduction. And another thing is that some latent entries will be there. Some latent entries relations will come up in this matrix, low rank approximation matrix, and that is applicable in latent semantic analysis. Okay. So SVD is useful in two things. One thing is about finding the principal components. That's one thing, and another thing is about finding the latent meanings, especially helpful in natural language processing. Okay. So that's what. And how do you say, for example, instead of having, say for example, there were a k number of features, okay, and you have taken a low rank approximation, okay, where r, you have taken low rank approximation where r is less than k. In that case, if you want to measure the quality, okay, of the, that is what is the difference between A and this low rank approximation matrix, okay, what's the difference between A and low rank approximation matrix, then you can just take this formula, just add the square of add the diagonals, the diagonals are, they are square of your diagonals are lambda 1, lambda 2, and you know that lambda 1 is the square of sigma 1. Okay, add the diagonals up to k divided by the diagonals of up to r, where r is the low rank approximation. Okay, and if they are approximately equal, then you say that this will be oh, just a minute, I think it should be 1 by where k is, oh sorry, where r is the actual length and k is less than r. K is our approximation, so k is less than r. So this is your original matrix, okay, and whereas this is the low rank approximation matrix, and if they are approximately say equal to 1, if they are both are r, then it is 1, okay. But if it is, say for example, if it is 0.9, that means by ignoring there is r minus k features, I have been able to reproduce my matrix A minus AK by 0.9. Okay, then I say that only 10% of information I have lost. Okay, that means those features which were available, okay, that is the features like for example I told you here, this lambda 1, lambda 2 up to lambda 20, even though they are there, but I have chosen only up to lambda 5, say lambda 1 to lambda 5. This has been by doing this I have been able to produce this A minus AK as 0.9, that is 90%. I have been able to reproduce. In that case, what does that mean? The meaning is lambda 6 to lambda 20, these features are not significant. That's what it means. Okay. So same thing. And see how it is applied in image processing. So I just take this. So you see that this is the curve that actually the total image. Okay. And you see that they have taken only up to this value. This sigma value they have taken only up to this. That is here. What is the rank? 25. They have taken as 25. For 25 itself, you see that you get a very good reproduction. Okay. So you see this is original. This is k equal to some big number, and this is k equal to 25. So you see that there's no much difference. So this is the error. This is the error. Okay. And here, when you take k as 10, k as 10 means just you see this much. This is 25. This is 10. You see that there is some blurring, but you can see you can reproduce the image. Okay. But the error is little bigger. Okay. And when you go here, you find when you just take only one value, the dominant value, dominant eigenvector value, then you see this is the error and this is the image. Okay, so that now you see because you have just taken only one value, only one eigenvalue, so that you don't get the exact image. The lot of the image goes into the error. Okay, and this is for 4 values. For 4 values, you can see you can reproduce the image to a certain extent. Okay, right. And this is for 10 values, still clear, and 25 values it will be better. Okay, like so. This is how it is used in image processing. Okay, and PCA, principal component analysis, just I've rushed through. So again the same thing. Say your data is there. Okay, this I already told you. So we find that this data is on both sides. It is extending, or the variance is on there both sides. But now when you do they have done with some example. So what they have done is this data has been taken. They made it as zero mean. They have taken it made as zero mean means xi minus x bar, means you take the average of x, and this is yi minus y bar. Take the average of y and subtract. So this data becomes a zero mean data. So this is data just shifts here, and your mean is zero. Mean is zero. Okay. So mean 0. Then what you do is then you find the covariance matrix of this. You have to find the covariance. Okay. So covariance matrix, you know how to find the covariance matrix. So covariance matrix is one where this diagonal elements are the variance of x and y, and here covariance means this item and this item. This is xy, and this is variance of yx. Okay, so this item, this item. So this is a covariance matrix. You find the covariance matrix, and then you find that the covariance matrix will look. So this is variance of x, this is variance of y, this is variance of xy, and this is variance of yx, and you find that they are square and symmetric. Square and symmetric. You find the eigenvalue, okay, and eigenvectors. These are the eigenvalue and eigenvectors. Now you find that the eigenvalue, this is bigger, okay, this is smaller. So meaning that this value is better. Okay, so this is lambda 1 and this is lambda 2. Lambda 1 is greater than lambda 2. In that case, this eigenvalue corresponds to which vector? I think this vector, this vector. So this will be a dominant vector, and this is, vector is this way. So this is, this is covariance matrix. So eigenvector. So eigenvector is this. So this eigenvalue corresponds to this vector, and this eigenvalue corresponds to this vector. Now you see that when you redraw the same thing, you will find that there is variance only in this vector, that is what we have found, and there's little variance here. Okay, so what we have done is this is the original data. There's a spread in this direction, but whereas after you do this reconstruction, you don't get that spread. It is only on one direction. That because this value is smaller than compared to this eigenvalue. That's the result. Okay, and as a result, you can see that this may be a small noise. You can take this as some noise. Okay, you can ignore that, but you can just take this value and you can from a 2 dimension you get a 1 dimension. Okay, from a 2 dimension you get a 1 dimension. So that's called this component is the principal component, whereas this is not the principal component. Okay, right. I think I can stop with this. Okay, so in the afternoon session I can again go ahead with something called linear discriminant analysis, LDA. Okay, then I will after having done that, then we will get into the other topic, that is about what is about the optimization. Okay, convex optimization, and we will see something about support vector machine. Okay, so I think we can for now we can I can stop here. If you have any questions, you can put it on the chat window. I can see that. Please give some examples of also reference books. Okay, reference books I'll share in the afternoon. Okay. Then about yeah, that's all. So reference books and this slides I can send it to you. Okay, that's not a problem. Yes, Madam Pumuri, Sir Paingudi, Madam.
What, yes, sir.
So we can stop with this today.
Yes, sir. Okay, sir.
And today afternoon session, I think I will start little early because I have a meeting at
Yes, sir. Yes,
3:30.
We will inform,
So
sir.
I'll 1:45 I will start the session. Okay.
Okay, sir.
1:45 to 3:15 we will go. Okay.
Okay, sir. Thank you so much for your informative session, sir. You have explained the mathematical essential for deep learning in detail and clearly for the participants. And also, I would like to thank all the participants. The feedback link is posted in the chat window. All are requested to fill the feedback form. So the next session starts at 1:45 p.m. today. It will be end at 3:30 p.m. Thank you all.